So we'll be looking into linear integrated circuits for this semester, and this is the syllabus, okay, that I have in front, which I'm sharing with you all. The course code, as you all know, is 19AC46, and the subject name is linear integrated circuits, right? So this is going to be for 3 credits, and your internals, as you all know, is going to be scaled down to 50 marks, and then your semester end examination is going to be for 50 marks. And you will be having co-curricular activity for this, okay, where you will be awarded the separate marks, okay, in addition to the curriculum. And these are the COs, okay, which means the course, okay, once you finish the course, what is going to be the outcome? What are you going to learn when you take up this course? Okay, so that is what is called as course outcome. So you'll be able to describe the basic building blocks and various parameters of an op-amp. So the short form of operational amplifier is nothing but an op-amp. Okay. Evaluate the DC and AC characteristics of these op-amps. So DC is your direct current and AC is your alternative current. Categorize the various op-amp linear and non-linear applications. Then you'll be able to analyze various signal processing circuits, and you will be able to look into voltage regulators, current sources. So which means these are examples of, I can probably give you the example of a fan, okay, where you have the regulator, right? So this is responsible in increasing the speed or decreasing the speed. So in the same fashion, we can then have these op-amps function as voltage regulators, okay, and current sources. The next thing that you can see here is design the filters using op-amps. So not only just regulating things, okay, but also we can look into the operational functions such as filters, right? So can you name a few filters? We have seen this, right? We've seen this, the third one, and the fifth one, filters. So filters, it can be low pass filter, high pass filter, band pass filter, okay, band stop filter. So these are the types of filters. Next, you will be even looking into some of the applications, like ADC is analog to digital converter, digital to analog converter. It can be used as a timer, right? So all this you can see in your traffic lights, right? Fine. Now this has 5 modules, okay, module 1 to 5, and in the first module we will be actually looking into the fundamentals, and we will be looking into the basics of op-amp, what are the parameters involved, and CMRR, common mode rejection ratio, okay, offset voltages, then how to use op-amps as DC amplifiers, as AC amplifiers, then about its impedance, okay, and then some of the applications, for example, voltage sources, current sources, integrator, differentiator, log, anti-log amplifiers, divider, summer, zero crossing detectors. All this, you'll be actually seeing in detail in the practicals. Okay, when you do your practicals, your communication lab practicals, you'll be seeing this in detail. And even in your DSP, you'll be actually designing filters, okay, using MATLAB. So these concepts are important. And you have RC, low pass and high pass circuit, active filters, then first and second order low pass and high pass filters, band pass filters. Then some of the other applications can be your timer, 555 timer. I think you would have used it in your labs, right? Digital electronics labs. And then phase lock loop, then your DAC and ADCs. So generally for digital to analog conversion, okay, we term it as DAC, and the reverse process as ADC, analog to digital conversion, right? So I hope this is very much clear as to what we are going to learn in this subject. And also these are the textbooks, okay? If possible, you guys can probably make a note of it, right? So these are the textbooks and the reference books, okay? So you can probably make a note or take a screenshot. So the first that we will be referring to is the operational amplifier and linear ICs by David A. Bell. So most of the topics, okay, for example, your unit 1, module 1, and the most part of module 2, okay. In fact, the whole of module 2 is also covered in the first textbook, okay, which is David A. Bell. And then some part of third module is also covered. Okay. These applications you can find in David A. Bell. And the other textbooks cover the remaining sections of your module. For example, the filters, phase lock loops, DACs, and ADCs. You can find it in Roy Chaudhary and Ramakant Gaikwad. So these are some of the best known textbooks for linear integrated circuits. So I hope all of you have taken note or taken a snapshot of this, right? Can I proceed?
Yes, sir.
Fine. Now we will just look at the basics. Okay, I will just run through the basic of op-amp. Okay, the first topic that I'll be starting, basic op-amp circuit. What does op-amp involve, and what are the properties of an op-amp? Why do we call it as an op-amp? Okay, so these we will be looking into. So now we will be just looking into a few basic stuff, okay, of op-amp. Okay, as I told, this is operational amplifier, okay, and in short we even call it as op-amp. Okay. Right. So I've just given here the structure of an IC, right? So you can just visualize it, and of course many of you have seen it, right? Yeah. So when we look into the basics, operational amplifiers are often referred to as op-amps, right? And they are very high gain amplifier circuits. Now the word amplifier itself, okay, what do you understand by the word amplifier?
That increases the
Yes,
signals.
correct. If the strength of the signal is too weak, then we use amplifiers to actually extend the capacity or the strength of the signal, right? Okay. Op-amps are very high gain amplifier circuits with two high impedance input terminals. So how many input terminals does it have? Two, right? And one low impedance output. So what is meant by impedance here? Can you tell me what is impedance?
Impedance is somewhat similar to resistance, sir, like opposing force.
Correct. So when I say there is high input impedance, which means that the input side will have high impedance, and when I say low impedance, which means whatever is in the circuit can freely flow out, okay, because there is no impedance, right? So the input terminals are identified as inverting input and non-inverting input. So there are two terminals here. Okay, one is inverting and the other one is non-inverting. Right. Okay. The basic op-amp circuit consists of a differential amplifier input stage. Now, this is important. Okay. So it has a differential amplifier input stage. Then it has in between a level shifting stage, and then an emitter follower at the output stage. So totally it is made up of three structures. Number one, it is made up of differential amplifier. It has a level shifter, right? And then number three, it has an emitter follower. Right? So these are some of the basic things that you should know. Now, why are we using an op-amp? So that our signal, whatever signal is there, it gets amplified and we get a proper signal at the output. Right? Okay. Any doubts here? Any doubts? You can always feel free to stop me, or you can ask any doubts at any point of time. So can I proceed?
Yes, sir.
Okay. Yes, sir.
Fine. Thank you. Operational amplifiers can be employed for many circuit applications. So as I told you, it can be used as a regulator, or it can be used as in a simplify timer. So these are some of the variety of things that you can do just with op-amp. Okay, so there is a lot of research also that can be taken up with respect to op-amp. By using various combinations of externally connected components. So using op-amp and some other components, you can actually use that for many other applications. So the usage will be high. The simplest of these are the voltage follower. Some examples I've mentioned here: voltage follower, non-inverting amplifier, inverting amplifier. So when I say inverting and non-inverting amplifier, inverting means whatever I'm giving signal, okay, so that gets inverted. Let's say, for example, at my input side, okay, I am giving this kind of sinusoidal wave. Okay, so let's say this is my input side. At my output side, at my V out, okay, if in case I'm using an say inverting amplifier, if I'm using an inverting amplifier, the output should be the reverse. Okay, so wherever it is high, okay, so that section becomes low. So when I use a non-inverting amplifier, then whatever is my input, the same thing comes across my output. Right? So I hope you have understood what is inverting and what is non-inverting. Right. So this is the basic structure, the symbol of an op-amp. So questions will be asked. Draw with the help of a symbol, explain its terminals and the basic operation of op-amp. So you can use this simple figure as your explanatory tool, right? So the symbol is like this. It looks like a triangle, okay? And as I mentioned, it has two inputs. One is called the non-inverting input and the other one is called inverting input. For the non-inverting input, okay, the symbol given here is plus. And for the inverting input, the symbol given here is minus. So as I mentioned previously, non-inverting and inverting, what do they do? If it's a high value at the start, here it's going to be low value, right? So similarly for the non-inverting terminal, right? Now this one needs to work, which means it needs some food to perform its functions. So it is given in the form of plus VCC and minus VEE. Okay. So let us say example, I can even give 5 volts. So this is going to be plus 5. Okay. And this is going to be minus 5. Unlike previously, we used to use VDD and ground, right? So this is not ground. This is -5. Here also you are giving the negative voltage. Here you're giving the positive voltage. So sometimes by referring, okay, we refer to it as plus or -5. So this +5 is referring to VCC, okay, and this -5 is referring to minus VEE. Right. Okay. Now this can range from 5 to 22 volts. Okay, so that's the range typically. Generally, I have seen, we using the amps in the range of 14 volts. Okay, so that should be the ideal level of voltages that can be used. So plus 14 we can use here and -14 we can use here. Or sometimes they even use 12 volts. Okay, fine. So here I'm giving my plus VCC, here minus VEE. I'm getting the output here, non-inverting input and the inverting input. So these two are the input terminals and one output terminal it has, right? And it has two supply terminals. So those supply terminals are your plus VCC and minus VE. Okay. Right. Now, let me just introduce you to a few more specifics of this op-amp. Okay. So the op-amps, it's an amplifier or buffers in general are drawn as a triangle in circuit schematic. You have seen that here, right? We use a triangle. There are two inputs, okay, inverting and non-inverting. We have seen that also, and one output terminal. Also, power connections, okay, to explicit ground. So if I have to connect few more stages here, some other circuit here, then I'll be using ground. Okay. So this is your pin number 2, pin number 3, 7 goes to plus VCC, and 4 goes to minus VEE. And at the 6th terminal, we take the output. So internally, this is how it looks. Okay, the notch should be here. So the notch faces at the first pin. Okay, so second and third, as I mentioned here, is your input. Right. So the same thing is what is mentioned here. Input 2, 3, right? And then you have your output here at 6, plus 7, plus for 7, and then minus for 4 here. So this is how it is connected. Fine. Now there should be some properties which actually say, this is an ideal op-amp. This is when I call that it is perfect, right? So we can understand that with the help of these points which I have put. So the ideal op-amp will actually have infinite voltage gain, which means lot of gain. Suppose you give 5 as your input, you might even get 500 as your output. So there is an enormous voltage gain. Okay. A voltage difference at the two inputs is magnified infinitely. Now, one thing you should understand here, as I mentioned in the previous section, it includes a differential amplifier. What is a differential amplifier? Suppose I give 5 volts here. Suppose 5 is given here, okay, and 3 is given here. So the difference is what? 2. So this 2 is what is going to get amplified, right? So that is the function of your differential amplifier. So the difference between the two inputs, that signal is amplified. Okay. So voltage difference at the two inputs is magnified infinitely because the voltage gain is what? Infinite. In truth, it is something like 2 lakh times. So it's going to be the difference between plus terminal and minus terminal is amplified by 2 lakh times, right? infinite input impedance, okay, which means it does not allow any current to flow inside. So that's why it has infinite input impedance. Okay, so this can be represented as Z. Okay, impedance can be represented as Z and infinite. In truth, about 10 raised to 12 ohms for FETs for the input op amps. So actually, we say infinite, okay, or we say very high input impedance, but then practically, you cannot design something infinite. So which means we take very high resistor, okay, so which is about 10 raised to 12. So technically speaking, there cannot be any current that can flow through because it's a very high resistance. Next, you have zero output impedance, which means rock solid independent of load. So either there is load or not, you're going to get a proper output. There is not going to be any disturbance in the output side because there is no impedance at all. It is a zero output impedance. So which means there is no resistance. You can say that it is 0 ohms. Roughly true up to the current maximum, usually 5 to 25 milliamps. Okay. So that should be the maximum that can be the levels of currents. Infinite fast, infinitely fast. Okay, so which means you can have infinite bandwidth. Okay, so which means what is a bandwidth? Bandwidth is a range of frequency, right? So we can say F1 is something, F2 is something. Then the difference between F1 and F2 is going to be your bandwidth, right? So in truth, it is actually limited to few megahertz. So this is talking with respect to frequency of operation. And the slew rate is limited to 0.5 to minus 20 volts per microsecond. Slew rate is nothing but the curve. Okay. So these are some of the things which define as to what is an op amp and what are its properties. Gain should be very high. Input impedance is very high. Low output impedance. In fact, you can just take down these main points. Okay. So that at the end of the day, you can recall as to what was taught in the class. And then infinitely fast, which means it can accommodate huge frequency because the bandwidth is high. Now, we generally use the term called feedback.
Right? So can you go to previous slide once?
Previous slide, yeah.
I'm just noting the points.
Yeah. So if a question is asked, what are the properties of an ideal op amp? So you can list out these. I've just made it as simple as possible. Okay, of course, there are many other properties as well, but the main differentiating factors, the differentiating points are these. Input side, infinite gain, infinite impedance, output side, zero impedance, and then it has a higher bandwidth. So higher the bandwidth, it can accommodate more frequency. Okay, so that's the basic idea. Can I move on?
Yes, sir. Done. Yes, sir.
Okay. Now, generally, we take feedbacks, right? Sometimes they might ask students, are you all following, right? So you will say, yes, sir. For example, your friend said, sir, please go back to the previous slide. So it's a kind of feedback. So why do we need feedback? So that we get to know as to what is happening, right? So there can be two kinds of feedback. Can be a negative feedback, okay, which we connect here, and then the positive feedback, right? Now let's understand what this feedback is. The internal op amp, okay, the formula is V out is equal to gain into, okay, whatever is the difference, right? So as I told you, the gain is infinite, and you have this plus terminal here, you have this minus terminal, which means plus is referring to inverting or non-inverting. What is it referring to? The plus symbol, to what is it referring to? Inverting or non-inverting?
Non-inverted.
Good. And minus is referring to inverting, right? So the difference between these two, so which means it is telling that this is actually a differential amplifier, right? And the gain, so gain into whatever is the difference. So I told you, right, so that 2 volts will be actually amplified. So if V plus is greater than V minus, the output goes positive, right? So if V minus is greater, then the output goes negative. So whichever is higher, okay, it can be either V plus or V minus, whichever is higher, accordingly it becomes inverting or non-inverting. A gain of 2 lakh makes this device practically useless. You really do not need so much of gain, right? So if suppose the difference 5 and 3 is 2, so 2 into 2 lakhs, which means 4 lakh times 4 lakh is the output. Of course, we are not going to use it anywhere, right? So we have to reduce this gain. So to reduce the gain, we actually use feedback. Okay. So why is feedback used? Feedback is used to reduce this infinite gain, because we are not going to use such huge gain. Such huge gain is not required at all. So in order to reduce this, what do? I slowly connect a terminal, okay, to its input side, and this gives me a negative feedback. So my infinite gain, okay, so my infinite gain will actually slowly be reduced to some stable gain. Okay, so that's the whole idea. So can I move forward? Have you taken down this formula and structure, the symbol?
Yes, sir.
Fine. Now here comes the necessity of using the negative feedback. Infinite gain would be useless except in the self-regulated negative feedback regime. So normally negative feedback seems bad and positive seems good, but in electronics, it's different. If I have a lot of positive feedback given, then there will be a lot of oscillations. Okay, are oscillations good in a circuit?
No, sir.
No, it is not at all good. I want a stable output, right? I do not want any oscillations. So which means my positive feedback is going to be ruled out, right? I'm not going to use a positive feedback. So we are going to use the negative feedback. Negative feedback is going to be used. So why are we using that? Because it brings in something called stability. So it can make your output as stable as possible, which means I am trying to nullify the oscillations as much as possible. Okay, as much as possible, I want to reduce these oscillations. Imagine hooking the output to the inverting terminal. Okay, so that is to minus terminal. If the output is less than Vin, it shoots positive. So which means if the output is less than Vin, okay, so if the output is less than this, so which means this is going to be greater. Okay, so if this becomes greater, then it will invert. So if it inverts, then it will be positive. If the output is greater than Vin, okay, so whatever output that you are giving here, if it is greater than the input voltage, then it shoots to negative, right? Just like the previous one we saw. The result is that output quickly forces itself to be exactly Vin. So as much as possible, they want to be as equal as possible. So here also, if it's Vin, it will try to be Vin here also. Okay, if I'm giving 6 volts here and 8 volts here, okay, so this will try to shoot up and try to match up with Vin value. So slowly it will try to make up to 8. So that is what it is. So I want you to take down these two important points. Okay. Now, number one, if the output is less than V in, it shoots to positive. If the output is greater than V in, it shoots to negative. Please take down these 2 points along with the feedback loop. So this is the importance, of having a negative feedback. So generally, when we talk in layman's words, he's giving a negative feedback, which means it's referring to something bad. But then here in electronics, that's not the way. Generally, like here we are referring to stabilizing things. Okay, so it is good. Negative feedback is good in electronics. Okay. So now let us just put a small load across. Okay. So load can be a resistor, or it can be anything. It can be an LED. Okay. So just put a small load and we will check as to what are the properties. Even if we load the output, okay, which is as pictured, okay, wants to drag the output to ground. So let us assume that we are getting some output here, and this output passes through the resistor and then through the ground. So even if we are connecting it to ground via resistor, what is going to happen? The op-amp will do everything it can with its current limitations to drive the output until the inverting input reaches Vin. Remember, I told you this will drive so that Vin also comes here. So that's why I told plus and minus, right? So it is, they want to be same. This Vin here should be same here. It tries to make it same. So that's the usefulness of this negative feedback. Next, the negative feedback makes it self-correcting. So if it is less, it's going to make it more. If it's more, it's going to reduce. In this case, the op-amp drives or pulls, if Vin is negative, a current through the load until the output is equal to Vin. So if it is less, then through the load, it is going to make sure that, okay, it's going to make sure that this levels here is increasing. Okay, the input level is increasing. So what we have here is a buffer can apply Vin to a load without burdening the source of Vin with any current. So you don't have to put any current here, okay, just to make sure that the Vin also comes here. Okay, so this will happen in an automatic way, okay, in a self-regulatory way. So that's why it's called self-correcting. Why is it correcting? Because it is checking for differences. There should not be any difference. If there is a difference, then through this feedback, it actually rectifies. Okay. So one important thing that you all should make note here is that op-amp output terminal, okay, it can either sink the current or source the current, not like inputs that have no current flow. Okay. So this can act as a current source or a current sink, okay, which means you can get current through this, or you can sink the current here. Okay, so there are a lot of applications with respect to op-amp. So is this clear? Can I move forward? What is a buffer, by the way? Buffer. Buffer will give you the same output, whatever was there in the input, but there is going to be a slight delay because of the device. Okay, let us say let's take UPS as an example. I think many of you would have uninterrupted power supply systems, right, at your home. So this can act, or this can be as an example of buffer. So why is it acting as a buffer? Whenever there is a power supply, okay, the load that we have, for example, television or fan or whatever, uses this electricity. Suppose there is no power line, okay, the power is down, then immediately this UPS kicks in, right, which means it will provide you the necessity voltages and current levels. So it is buffering, or it is storing the current using its batteries, right? So this is able to pitch in so that there is no gap in your work, right? So that is a buffer. So whatever is in the input, the same thing you will get at your output side. So the other example that we can think of is, let's say you want to actually, let's say I'm talking very fast, okay, so you want to slow down. So you have in this videos, you have the option to slow down the pace, right, or you can fast forward, right, so that it moves fast. So buffer is something where you can actually have the communication done without any loss. Okay, so this holds the information, and then it passes on. So you can extract it fast, or you can take it slow. So that's the meaning of buffer. I hope you're getting the right. What is buffer, all of you? Yes.
So could you please repeat?
Yeah, buffer is something where it pitches in. Let us take a microprocessor, for example. Okay, so if the microprocessor is functioning at a very high speed, say about 1.5 gigahertz, that's the operation frequency. Example, I'm just giving you numbers, and you have another peripheral device, or some device that you have connected to the microprocessor, which is having just about 800 megahertz. Now gigahertz is higher, right? So which means the operation of your microprocessor is very high compared to your other device which is connected, right? So the speed is high. So we want to make sure that whatever output is given by the microprocessor is taken by someone, stored, and those values are utilized later. Okay, so that is called a buffer. Able to understand? So that there is no loss of information. There is no loss of information. Now suppose if I'm not able to catch up with the speed of microprocessor, then I might lose some of the signals, right? I do not want that to happen. So in that case, I'm going to use a buffer. Okay, is that clear?
Yes, sir.
Fine. Okay, so moving on, I think we will probably take this up in the next class, the positive feedback, right? And we will discuss positive feedback and some of the important rules that we have to follow, right? And probably I will even take a few numerical examples with regards to the design of op-amp circuit, right? So I think we will stop here, and we will get back. We'll continue our discussions in the next upcoming classes.